Deep in the darkness of interstellar space, racing toward our solar system at tens of thousands of kilometers per hour, astronomers have detected something that should be impossible. Something that has never been observed in any solar system comet, ever. We have always believed we understood the basic chemistry of these ancient comets, nickel and iron bound together since the formation of stellar systems, released together when solar heating awakens a comet's frozen surface. But 3I Atlas follows different rules entirely. Spectroscopic analysis reveals neutral nickel emissions streaming from this cosmic visitor, but the iron signatures that should accompany them are completely absent. However, pure nickel is a familiar phenomenon in terrestrial metallurgy, where it is obtained through refining. This raises a key question. Is this object a product of space manufacturing? While government space agencies speak in careful diplomatic language about safe trajectories and ongoing analysis, the preprint papers tell a different story. Tonight, we investigate what scientists aren't telling us about this interstellar visitor. We will examine the spectroscopic evidence, decode the institutional silence, and explore why some researchers whisper about possibilities that stretch far beyond conventional science. Prepare yourselves. We begin. Chapter 1. Nickel in the Dark. The cosmos has a way of keeping its most intriguing secrets wrapped in the language of spectroscopy. In the early morning hours of August 15th, 2025, astronomers peering through the European Southern Observatory's Very Large Telescope in Chile noticed something that shouldn't exist. There, dancing across their computer screens in the form of precise wavelengths of light, were the unmistakable signatures of neutral nickel atoms streaming from Comet 3I Atlas. But here's what made seasoned scientists pause mid-coffee. The iron lines that should have accompanied those nickel signatures were nowhere to be found. In our solar system, nickel and iron are cosmic siblings. They form together, travel together, and when a comet heats up enough to release one, you almost always see both. It's like finding footprints in snow from only one boot. The universe, it seems, doesn't usually separate these metallic twins without a very good reason or a very unusual process. What makes this discovery particularly unsettling is not just the scientific anomaly itself, but the careful way it's being discussed in academic circles. When you read through the preprint papers posted on Arxiv, the platform where scientists share their findings before peer review, you'll notice something curious. The language is unusually cautious, even for astronomy. Phrases like mechanism uncertain and unusual physics or chemistry pepper the technical documents like diplomatic warnings. The instrument trail tells its own story. Teams using the ultraviolet and visual Echelle spectrograph and X-shooter instruments at the Very Large Telescope have independently confirmed these nickel emissions. They've also detected the emergence of cyanide, that's CN to chemists, in mid-August spectra. These aren't the kind of observations you misinterpret or accidentally fabricate. Multiple instruments, multiple teams, consistent results. Yet if you scan the mainstream headlines about 3I Atlas, you'll find a curious disconnect. Some outlets hint at alien possibilities with the subtlety of a foghorn, while the actual scientific papers read like diplomatic cables, technically precise but emotionally sterile. The contrast invites a question. What exactly are we looking at when we stare into the spectroscopic soul of this interstellar visitor? There's another puzzle wrapped inside this cosmic riddle. 3I Atlas is shrouded in a coma. That's the fuzzy atmosphere around its nucleus, dominated not by water vapor like most comets, but by carbon dioxide. This CO2 shroud acts like a cosmic fog bank, making it nearly impossible to see the actual solid nucleus underneath. It's as if the comet is wearing a chemical cloak, revealing only what it chooses to show us. The James Webb Space Telescope has confirmed what ground-based observations suggested. This object produces carbon dioxide at rates that dwarf its water production by ratios rarely seen in nature. For context, Most comets are cosmic snowballs with a bit of dry ice mixed in. 3I Atlas appears to be the opposite, a dry ice ball with just a hint of snow. So we're left with a series of interconnected mysteries. A comet that produces nickel without iron. A composition dominated by carbon dioxide rather than water. A nucleus hidden behind its own emissions like a magician behind smoke and mirrors. And most intriguingly, a scientific community that seems to be choosing its words with unusual care. The guiding question that will follow us through this investigation is deceptively simple. Are we witnessing a natural quirk of cosmic chemistry and formation, or something that challenges our understanding of what's possible in nature? The evidence, as we'll see, doesn't yet point definitively in either direction, but it does whisper of possibilities that stretch the boundaries of conventional comet science. The cosmos, after all, has been whispering in nickel, and sometimes the quietest voices carry the most important messages. Chapter 2. Meet 3I Atlas. To understand why 3I Atlas has astronomers reaching for their most diplomatic language, we first need to understand what makes this visitor so fundamentally different from anything in our cosmic neighborhood. The designation itself tells a story. 3I marks it as only the third confirmed interstellar object ever detected passing through our solar system. Following the mysterious cigar-shaped 1I/Oumuamua in 2017 and the more conventional Comet 2I/Borisov in 2019. The Atlas portion honors the asteroid terrestrial Impact Last Alert System, specifically the station at Rio Hurtado, Chile, where this cosmic wanderer was first spotted on July 1st, 2025. Picture the scene. Automated telescopes scanning the southern sky, their cameras capturing millions of points of light each night, when suddenly the computer algorithms flagged something moving with a velocity and trajectory that didn't belong to our solar system's gravitational embrace. The official designation reads C/2025 N1 Atlas, but the international astronomical community quickly recognized its interstellar nature and promoted it to 3I Atlas. This promotion isn't merely bureaucratic, it represents confirmation that this object originated somewhere else entirely, in a stellar system potentially hundreds or thousands of light-years away, and is now making what amounts to a one-time flyby through our celestial neighborhood. The mathematics of its trajectory tell an unambiguous story. 3I Atlas follows what astronomers call a hyperbolic orbit, a path so energetic that our sun's gravity can bend but not capture it. Unlike the elliptical orbits of solar system natives, this trajectory is open-ended, a cosmic highway that leads from interstellar space around our sun and back out into the galactic void. No return trips, no second chances for detailed study. From Earth's perspective, this interstellar visitor poses absolutely no threat. Its closest approach to our planet will be approximately 1.8 astronomical units, roughly 270 million kilometers away. To put this in perspective, that's farther than the distance between Earth and the Sun. Mars, during its closest approaches to Earth, gets within about 55 million kilometers. 3I Atlas will maintain a respectful cosmic distance, like a polite visitor who admires your garden from the sidewalk rather than trampling through your flower beds. The timing of its solar encounter adds another layer to this cosmic story. Perihelion, the point of closest approach to the Sun, is scheduled for around October 30th, 2025, at approximately 1.4 astronomical units from our star. That places it just inside Mars's orbital distance, close enough to receive significant solar heating, but far enough away to avoid the extreme conditions that might completely vaporize a small nucleus. Speed-wise, 3I Atlas is racing through our solar system at tens of kilometers per second relative to the Sun. Those racing through headlines you might have seen are technically accurate, but they can be misleading. This velocity is entirely normal for interstellar objects. What makes it remarkable isn't the speed itself, but the fact that this speed originated from motion through the galaxy rather than from our sun's gravitational acceleration. The timeline of visibility presents both opportunities and challenges for Earth-based observers. After perihelion in late October, 3I Atlas will appear to move closer to the Sun as seen from Earth, making observations increasingly difficult through November as it approaches what astronomers call solar conjunction, the point where it disappears behind the Sun's glare. However, this celestial game of hide-and-seek ends in early December 2025, when the comet emerges on the other side of the Sun for what may be our final extended observation period. One of the most frustrating aspects of studying 3I Atlas is how little we can directly observe of its nucleus. The Hubble Space Telescope, despite its extraordinary capabilities, can only establish an upper limit of approximately 5.6 kilometers for the nucleus diameter. This isn't a failure of our most advanced space-based observatory, it's a testament to how effectively the comet's own emissions obscure its solid core. Imagine trying to study a campfire by looking at the smoke rather than the flames. That's essentially what we're doing with 3I Atlas. The nucleus itself remains hidden behind its own coma, that fuzzy atmosphere of gas and dust that extends tens of thousands of kilometers from the tiny solid center. This observational challenge becomes even more significant when we compare 3I Atlas to its interstellar predecessors. 1I/Oumuamua appeared to be largely inert, producing no detectable coma despite its bizarre elongated shape and mysterious non-gravitational acceleration. 2I/Borisov, on the other hand, behaved exactly like a solar system comet, complete with a beautiful tail and composition matching what we'd expect from our own Kuiper belt objects. 3I Atlas occupies a middle ground that's somehow more puzzling than either extreme. It's clearly active, producing the gas and dust emissions we associate with comets. But the chemistry of those emissions tells a story unlike any comet we've studied before, a story written in nickel lines without iron, in carbon dioxide ratios that dwarf water production, and in cyanide signatures that emerged precisely when theoretical models suggested they should. As we'll discover, this cosmic visitor's reluctance to reveal its secrets may be the most telling characteristic of all. Chapter 3: The Carbon Dioxide Shroud. Most comets are cosmic snowballs with a secret. Beneath their dirty ice exteriors lies a chemistry dominated by water, the molecule that makes Earth's oceans possible and life as we know it thinkable. 3I Atlas, however, seems to have read a different script entirely. The James Webb Space Telescope's spectroscopic analysis reveals a coma dominated not by water vapor but by carbon dioxide, and in ratios that stretch the boundaries of what astronomers consider typical for these ancient time capsules. The numbers, while still being refined through peer review, suggest a carbon dioxide to water ratio of approximately 8:1. To understand how extraordinary this is, consider that most solar system comets produce water and carbon dioxide in roughly opposite proportions. It's like discovering a snowman made primarily of dry ice with just a dusting of regular snow, technically possible, but so unusual it demands explanation. This carbon dioxide dominance creates what we might call a cosmic fog bank. Unlike water vapor, which is relatively transparent at many wavelengths of light, carbon dioxide forms a dense, optically thick shroud around the nucleus. The result is that even our most sophisticated instruments struggle to peer through this chemical veil to glimpse the solid core underneath. It's as if 3I Atlas is wearing a cloak woven from its own emissions, revealing only what it chooses to show us. The Ferrex mission's preliminary observations add another piece to this puzzle. Their imaging shows an extended carbon dioxide coma with no obvious jets or streamers, those characteristic features that usually point back toward active regions on a comet's nucleus. Instead, 3I Atlas appears to be outgassing uniformly from its entire surface, or at least in a pattern so symmetric that individual jets blend into a smooth, featureless glow. The Hubble Space Telescope's images reinforce this sense of concealment. What we see is essentially a dusty cocoon, with background stars streaked into trails due to the telescope's tracking of the comet's motion. The nucleus itself remains stubbornly invisible, hidden somewhere within that cocoon like a cosmic Russian doll whose innermost layer refuses to be revealed. Several working hypotheses attempt to explain this carbon dioxide dominance, but each raises as many questions as it answers. One possibility involves the comet's formation environment. If 3I Atlas originated in a stellar system with a different temperature profile than our own, perhaps around a star cooler than our Sun, it might have formed near what astronomers call a carbon dioxide ice line. In such an environment, carbon dioxide would freeze out before water, potentially creating objects with compositions dramatically different from our solar system's comets. Another hypothesis focuses on thermal evolution and surface physics. Some comets develop insulating crusts over their lifetimes, layers of dust and processed organic materials that act like cosmic thermos bottles. Such a crust might suppress water vapor outgassing, while allowing the more volatile carbon dioxide to escape more easily. As 3I Atlas approaches the Sun, this selective outgassing could create the skewed chemistry we observe. The production rates themselves tell a story of a small but active nucleus. While the absolute numbers vary depending on the instrument and analysis method, a reminder that we're watching science in real time as calibrations are refined, the order of magnitude suggests a modestly sized object, producing gas at rates consistent with its apparent size. There's nothing here that screams impossible, but everything whispers unusual. Media coverage has latched onto the cloak metaphor with enthusiasm, sometimes implying a deliberate concealment rather than a natural consequence of chemistry and physics. This linguistic choice reveals something about how we process cosmic mysteries. When nature behaves in unexpected ways, we tend to anthropomorphize the phenomenon, attributing intention where there may be only the inevitable result of unfamiliar physics playing out in an alien environment. The carbon dioxide shroud also complicates every other measurement we want to make. Dust production rates, nucleus rotation periods, surface temperature mapping, the search for jets or active regions, all of these observations become more challenging when filtered through a dense, chemically active atmosphere. It's like trying to study a lighthouse bulb from inside a thick fog. You can see that something bright is happening, but the details remain maddeningly obscured. What makes this even more intriguing is the timing of our observations. Different instruments observing at different epochs can produce apparently contradictory results that later reconcile as we understand the temporal evolution of the coma. A spectrum taken in July might show 1 carbon dioxide to water ratio, while an August observation reveals a different value, not because the measurements are wrong, but because comets are dynamic systems that change as they approach and recede from the Sun. The carbon dioxide mystery deepens when we consider the implications for the nucleus composition. If the coma is dominated by carbon dioxide, what does that tell us about the solid ice mixture from which these gases are sublimating? Are we looking at a fundamentally different type of planetary building block, one that formed under conditions so unlike our solar system's early environment that it challenges our models of how planetary systems assemble? Or perhaps, as we'll explore further, the carbon dioxide shroud is telling us something else entirely, something about processes that don't typically occur in nature, or about a visitor whose origins may be more exotic than even interstellar space usually provides. The fog bank surrounding 3I Atlas isn't just obscuring our view of its nucleus. It may be obscuring our understanding of what's possible in the cosmos itself. Chapter 4. The Official Line. When government space agencies speak about 3I Atlas, their language carries the careful precision of diplomatic communiques. NASA's official statements read like a checklist designed to inform without alarming. Interstellar comet, safe trajectory, perihelion approximately October 30th, 2025, at roughly 1.4 astronomical units from the Sun. Closest Earth approach, approximately 1.8 astronomical units. No threat to our planet. The facts are presented with the emotional temperature of a weather report, technically accurate, reassuringly mundane. This measured tone isn't accidental. Space agencies learned hard lessons from previous encounters with unusual celestial visitors. The public reaction to Oumuamua's bizarre characteristics spawned everything from serious scientific debates about hydrogen icebergs to wild speculation about alien spacecraft. With 3I Atlas showing its own collection of anomalous properties, NASA and its international partners have apparently decided that conservative communication is the better part of valor. The European Space Agency echoes NASA's cautious approach, emphasizing the same safe distances and lack of threat to Earth while noting the object's speed and late October perihelion timing. Their press releases read like exercises in measured reassurance, providing enough information to satisfy public curiosity while avoiding anything that might fuel speculative fires. The Minor Planet Center, which serves as the official clearinghouse for observations of asteroids and comets, has been similarly restrained. Their minor planet electronic circulars dutifully record astrometric observations, the precise positions needed to calculate and refine the object's trajectory, but avoid interpretive commentary. They're the cosmic equivalent of court stenographers, recording what happened without editorial comment. The Hubble Space Telescope program's public communications follow a similar pattern. Their Astronomy Picture of the Day feature shows the comet as a fuzzy blob against star-streaked backgrounds, with captions that emphasize the hyperbolic orbit and size constraints while carefully avoiding speculation about the object's unusual properties. Even when presenting visually spectacular images, the accompanying text maintains a tone of scientific neutrality. This conservative approach extends to the James Webb Space Telescope team's blog posts and press releases. Despite conducting some of the most detailed spectroscopic observations of 3I Atlas, their public communications stick to safe harbor phrases, analysis underway, preliminary results, further observations planned. They link to preprint papers rather than making bold claims, letting the technical literature speak for itself while avoiding institutional endorsement of any particular interpretation. Behind this cautious public face lies a more complex reality. The same agencies funding detailed observations with the world's most advanced telescopes are clearly taking 3I Atlas seriously enough to dedicate precious observing time from instruments that are oversubscribed by factors of 10 or more. The James Webb Space Telescope doesn't point at random objects. Every minute of its operation represents thousands of dollars and months of competitive proposal processes. The visibility timeline adds urgency to these observations. 3I Atlas will likely become too close to the Sun for safe observation from Earth sometime in late September, remaining hidden behind solar glare until early December 2025. This creates a narrow window for detailed study before perihelion, and another brief opportunity afterward when the comet emerges from conjunction. The agencies know this is essentially a one-shot deal. Miss the opportunities this year, and 3I Atlas disappears into interstellar space forever. What's particularly interesting is what the official statements don't say. There's no mention of the nickel emission lines detected by European Southern Observatory teams, no discussion of the unusual carbon dioxide to water ratios, no acknowledgement of the cyanide detections or their timing. This isn't necessarily secrecy, it's standard practice to let peer review processes run their course before making official pronouncements about potentially significant discoveries. The glossary-heavy nature of official communications also serves a strategic purpose. By carefully defining terms like perihelion, astronomical unit, coma, and production rate, agencies can provide education while maintaining focus on established science rather than speculative interpretations. It's a way of keeping the conversation grounded in measurable phenomena rather than letting it drift into theoretical territory. Multi-observatory coordination tells its own story about institutional priorities. The James Webb Space Telescope, Hubble Space Telescope, and SPHERICS missions have all been directed to observe 3I Atlas, suggesting high-level interest despite the measured public tone. When space agencies coordinate observations across multiple billion-dollar facilities, they're making a statement about scientific importance, even if they won't explicitly say so in press releases. The peer review timeline creates additional tension between public curiosity and institutional caution. Preprints appear on ArXiv within days or weeks of observations, but formal publication in peer-reviewed journals can take 6 months or more. During this gap, the most interesting findings exist in a scientific limbo, significant enough for researchers to share with colleagues, but not yet validated enough for agencies to stake their reputations on. Perhaps most tellingly, the absence of bold claims in official communications shouldn't be interpreted as evidence against extraordinary possibilities. Space agencies learned from Oumuamua that unusual objects can spawn unusual theories, some of which later prove correct, and others which prove embarrassingly wrong. In this environment, saying, "We don't know yet," becomes both intellectually honest and institutionally prudent. The official line, in other words, may be less about what space agencies know and more about what they're willing to say before the scientific process runs its complete course. Chapter 5. The Lab Notes and Preprints. While government agencies practice diplomatic restraint, the scientific community operates in a different realm entirely, one where curiosity moves faster than institutional caution and discoveries are shared through preprint servers before bureaucratic approval processes can slow them down. In the case of 3I Atlas, this parallel universe of laboratory notes and preliminary findings tells a far more intriguing story than official press releases suggest. The European Southern Observatory teams working with the Very Large Telescope's UVs and X-Shooter instruments have been remarkably forthcoming in their RXiv submissions. Their mid-August observations documenting neutral nickel emission lines without corresponding ion signatures represent the kind of finding that makes experienced spectroscopists double-check their calibrations. When multiple independent instruments confirm the same anomalous result, it moves from interesting if true to demanding explanation. The timing of these observations matters enormously. Early July spectra captured what amounts to a baseline, 3I Atlas at greater solar distance, with relatively quiet, outgassing and conventional comet behavior. The mid-August observations, as the comet moved closer to the Sun and its surface temperatures began rising, showed the emergence of both the nickel lines and detectable cyanide emission. This temporal correlation suggests we're watching chemical processes unfold in real time, driven by increasing solar heating. An independent confirmation of the cyanide onset appeared in a September 3rd letter to the astronomy community, reporting the mid-August emergence consistent with Very Large Telescope observations and additional confirmations from Lowell Observatory. When multiple research groups using different telescopes report the same temporal evolution of spectral features, it becomes difficult to dismiss as instrumental artifacts or calibration errors. The SPHERICS preliminary note adds another dimension to this emerging picture. Their observations of an extended carbon dioxide coma with no obvious jets or streamers complement rather than contradict the spectroscopic findings. What we're seeing is a remarkably uniform outgassing pattern that produces unusual chemistry, carbon dioxide dominance, nickel without iron, and evolving cyanide production, all from what appears to be a small, featureless nucleus. These preprint submissions follow a well-established rhythm in astronomy. Observations are made, data are processed and analyzed. Preliminary findings are shared with the community through Arxiv, and then the formal peer review process begins. This system allows for rapid dissemination of potentially important discoveries while maintaining the quality control that comes from expert evaluation. It also means that the most interesting findings often appear in technical papers months before they make their way into official agency statements. The production rate calculations illustrate both the power and the pitfalls of this preprint system. Different research groups, using different instruments and slightly different analysis techniques, can produce measurements that appear to disagree, not because anyone is wrong, but because the absolute calibration of production rates depends on assumptions about nuclear size, outgassing patterns, and atmospheric models. These apparent discrepancies usually resolve themselves as the analysis techniques converge and more data become available. What's particularly fascinating is how blog posts and informal commentary have begun interpreting these preprint results. Some analysis pieces suggest that the combination of unusual chemistry and hidden nucleus might indicate industrial processes or technological artifacts. These interpretations go well beyond what the data currently support, but they illustrate how quickly scientific observations can be extrapolated into speculative territory. The cadence of observations matters enormously for understanding comets, which are fundamentally dynamic systems. A spectrum taken in July shows one snapshot of chemistry and activity. An August spectrum reveals changes driven by increasing solar heating. September observations capture further evolution as the comet approaches perihelion. Only by combining multiple epochs can we understand the full story of how 3I Atlas responds to its changing thermal environment. Different instruments contribute different pieces of this puzzle. Ultraviolet and visible light spectroscopy excel at detecting metallic emissions like nickel and iron. Infrared observations from space-based telescopes can penetrate dust better and detect molecular emissions that are invisible to ground-based observations. Radio telescopes might detect molecules that don't emit invisible light. Each wavelength range tells part of the story, but the complete picture emerges only when all these observations are combined. The peer review process that follows preprint submission serves as both quality control and reality check. Expert reviewers examine methodology, question assumptions, and suggest alternative interpretations. This process typically takes months, during which preliminary findings might be refined, strengthened, or occasionally overturned entirely. In the fast-moving world of comet observations, where objects appear and disappear on timescales of months, this creates inevitable tension between scientific rigor and public curiosity. What emerges from this laboratory phase is a picture of 3I Atlas that's simultaneously more detailed and more puzzling than official summaries suggest. The nickel detections appear robust. The carbon dioxide dominance seems real. The temporal evolution of chemical signatures follows predictable patterns driven by solar heating. But the underlying mechanisms that produce these observations, particularly the decoupling of nickel from iron, remain mysterious. The lab notes, in other words, are humming with activity and generating more questions than answers. And in science, that's often exactly where the most interesting discoveries begin. Chapter 6. Interpreting nickel, natural versus unnatural. The detection of neutral nickel emission lines in 3I Atlas's spectrum represents something like finding a single type of fingerprint at a crime scene, technically clear evidence of what happened, but puzzling in its isolation. In solar system comets, nickel and iron emissions appear together with the reliability of a chemical law. When comets heat up enough to sublimate metallic grains embedded in their ice, both metals typically appear in spectroscopic observations because they form together in stellar nucleosynthesis and remain together through the planetary formation process. 3I Atlas breaks this rule and the question becomes whether we're witnessing exotic but natural chemistry or something that challenges our understanding of what's possible without technological intervention. The natural pathways for nickel-iron decoupling, while speculative, aren't beyond the realm of known chemistry and physics. One possibility involves selective volatility, the idea that under specific temperature and pressure conditions, nickel-bearing compounds might sublimate while iron-bearing compounds remain locked in solid form. This could occur if the comet's composition includes organic molecules that preferentially bind with iron, keeping it from escaping into the gas phase while allowing nickel to outgas freely. Another natural mechanism might involve surface chemistry driven by space weathering. Over millions of years in interstellar space, cosmic ray bombardment and exposure to the interstellar medium could chemically alter surface materials in ways that change how metals are bound and released. If 3I Atlas spent significantly longer in interstellar space than typical Oort cloud comets spend between stellar encounters, such weathering could create surface chemistry unlike anything we see in solar system objects. The compositional heterogeneity hypothesis suggests that 3I Atlas might have formed in a stellar environment with different metallicity than our solar system. Some stars form with different ratios of heavy elements, depending on their location in the galaxy and the composition of the molecular cloud that birthed them. A comet formed around a metal-poor star might naturally contain nickel and iron in unusual proportions or chemical forms. Perhaps the most intriguing natural possibility involves carbonyl chemistry. In environments rich in carbon monoxide, which 3I Atlas appears to be, given its carbon dioxide dominance and cyanide production, transient metal carbonyls might form under specific conditions. Nickel carbonyl is a known compound that's more volatile than most iron carbonyls, potentially creating conditions where nickel escapes into the coma while iron remains bound to the nucleus. This mechanism remains entirely speculative and would require laboratory confirmation, but it represents the kind of exotic chemistry that might occur in unusual thermal and chemical environments. The unnatural pathway, stated clearly as a thought experiment rather than a conclusion supported by evidence, would require some form of technological processing that selectively concentrates or releases nickel. Industrial processes on Earth do create nickel-rich alloys and compounds with minimal iron content. Stainless steel production, electroplating, and specialized metallurgy all involve techniques that could, in principle, create materials with the chemical signatures we're observing. The question isn't whether such processing is possible, it's whether there's any evidence for it beyond the nickel detections themselves. A responsible evaluation of the engineered hypothesis would require multiple independent lines of evidence. Isotopic ratios that differ from solar system norms might suggest nucleosynthesis processes that don't occur naturally. Structured radar echoes could indicate geometric regularity inconsistent with natural objects. Non-gravitational accelerations with patterns that suggest propulsion rather than outgassing would be compelling. Radio emissions synchronized with the object's geometry might indicate artificial transmission. None of these additional technosignatures have been reported for 3I Atlas. The observational context matters enormously for evaluating these possibilities. Solar system comets do occasionally show unusual metal line ratios, though typically not as extreme as the nickel without iron pattern observed in 3I Atlas. The decoupling isn't physically impossible, it's statistically unusual. This distinction matters because unprecedented doesn't automatically imply artificial, especially when dealing with objects from stellar environments that might differ significantly from our local chemical neighborhood. What would strengthen the natural case is reproducibility across multiple instruments and observing epochs, combined with theoretical models that can account for the observations without invoking exotic processes. If the nickel emissions continue to appear consistently as 3I Atlas approaches perihelion, and if the thermal evolution matches predictions from models of selective outgassing or unusual surface chemistry, the case for natural but exotic chemistry becomes more compelling. Conversely, what would strengthen consideration of technological origins would be the appearance of additional anomalies that collectively point toward artificial processes. A single unusual chemical signature might be explicable through natural means, but multiple independent anomalies that all suggest technological origins would be much harder to dismiss. The key word is independent. The anomalies would need to be explainable by technology, but not by any natural process. The commentary suggesting industrial nickel signatures represents interesting speculation rather than scientific consensus. Such ideas deserve consideration as hypotheses to be tested rather than conclusions to be accepted, and they must be held to the same evidentiary standards as any other scientific claim. The burden of proof for extraordinary claims remains extraordinarily high, regardless of how compelling the speculation might be. Current observations provide one piece of a much larger puzzle. As 3I Atlas continues its approach to perihelion, additional data will either support or refute various hypotheses about its nickel emissions. Peer review processes will evaluate the robustness of the original detections. Cross-calibration between different instruments will test whether the observations are reproducible. Theoretical work will explore whether known chemistry and physics can account for what we're seeing. For now, the nickel whispers of possibilities without shouting conclusions, and in the careful language of science, whispers often carry more weight than proclamations. Chapter 7. Why Scientists Hold Back. The path from raw astronomical data to confident scientific conclusions follows a labyrinthine route that the public rarely sees, involving calibrations within calibrations, systematic error analysis that can take longer than the observations themselves, and institutional review processes designed to prevent the kind of spectacular mistakes that can end careers and undermine public trust in science. When it comes to 3I Atlas, this normally invisible machinery of science becomes particularly relevant because the observations are both technically challenging and potentially significant enough to reshape our understanding of interstellar objects. Consider the basic pipeline that transforms photons collected by a telescope into the spectroscopic signatures that drive scientific conclusions. First, the raw data must be calibrated against known standard stars to establish accurate wavelength and flux scales. Then the sky background, including everything from atmospheric emission lines to scattered light from nearby sources, must be subtracted with mathematical precision. Only then can astronomers begin the process of identifying specific spectral lines and measuring their intensities relative to the continuum background. Each of these steps introduces potential systematic errors that can masquerade as genuine signals. A small error in wavelength calibration might shift an apparent nickel line to a different element entirely. Incomplete sky subtraction could create false emission features or suppress real ones. Continuum placement, determining what counts as the baseline against which emission lines are measured, can dramatically affect the apparent strength of weak spectral features. When claims of unusual chemistry rest on precisely these kinds of measurements, extraordinary care becomes essential. The telescope time allocation system adds another layer of institutional caution. Observing time on facilities like the Very Large Telescope or James Webb Space Telescope is awarded through competitive processes that can take months of preparation and review. When astronomers receive this precious resource, they typically have proprietary periods during which they can analyze their data without external pressure. This system encourages thorough analysis rather than rushed conclusions, but it can also create frustrating delays between observations and public announcement of results. The signal-to-noise ratio considerations become particularly critical when dealing with weak spectral features near the detection threshold. The same dataset can appear to show strong emission lines or no emission at all, depending on how the analysis is conducted. Different continuum fitting techniques, different methods for combining multiple exposures, even different software packages for data reduction can yield seemingly contradictory results from identical observations. Multiple independent teams must verify unusual claims before the scientific community accepts them as robust. Reputation and replication concerns loom especially large in the aftermath of the 1I/Oumuamua debates, where initial observations of an unusual acceleration spawned theories ranging from hydrogen icebergs to alien spacecraft. Some of those theories were eventually supported by additional analysis, while others were quietly abandoned as better data became available. The experience taught the astronomical community that interstellar objects can generate intense public interest and scientific controversy in equal measure, making careful evaluation of claims more important than rapid announcement. The peer review process, while often frustratingly slow, serves as quality control that can catch errors invisible to the original research teams. Expert reviewers examine methodology, question assumptions, suggest alternative interpretations, and occasionally identify systematic errors that invalidate entire analyses. This process can take months or even years, during which preliminary findings remain in scientific limbo, interesting enough to discuss among colleagues, but not validated enough for institutional endorsement. Observing geometry adds temporal complexity to these systematic concerns. The apparent strength of spectral lines depends not just on the physical processes producing them, but on the viewing angle, phase angle, and distance between Earth and the comet. An emission line that appears strong in July observations might seem weak in August data, not because the underlying physics has changed, but because we're viewing the same process from a different perspective or at a different distance. Inter-instrument cross-checks provide essential validation but require careful attention to systematic differences between facilities. The Very Large Telescope's UVS instrument operates differently from the X-Shooter spectrograph, which in turn has different characteristics from space-based instruments like those on James Webb or Hubble. Confirming a detection across multiple instruments requires understanding how each facility's unique systematic errors might affect the apparent strength or wavelength of spectral features. The James Webb Space Telescope team's blog posts exemplify this institutional caution. Despite conducting some of the most detailed observations of 3I Atlas, their public communications stick to phrases like analysis underway and preliminary results. They link to preprint papers rather than making institutional claims, letting technical literature speak for itself, while avoiding situations where the space agency might need to retract or revise public statements if peer review reveals problems with initial analyses. Visual representations of the same data can tell dramatically different stories depending on processing choices. The same spectrum can be made to emphasize weak emission lines by expanding the vertical scale, or to de-emphasize them by showing the full dynamic range of the data. Different continuum fits can make emission features appear or disappear entirely. When dealing with potentially significant discoveries, researchers must ensure their data presentation choices reflect the genuine strength of the evidence rather than their hopes about what the data might show. The bottom line is that scientific caution doesn't indicate cover-up or conspiracy. It reflects hard-won wisdom about how easy it is to fool ourselves when dealing with complex data near the limits of instrumental sensitivity. In astronomy, where objects appear and disappear on timescales that don't accommodate lengthy analysis, this creates inevitable tension between scientific rigor and public curiosity. But it also ensures that when astronomers do make strong claims about unusual objects like 3I Atlas, those claims rest on foundations solid enough to support the weight of extraordinary implications. Chapter 8: Media versus Methods. The chasm between how scientific discoveries unfold in laboratory notebooks and how they appear in public media represents more than just a translation problem. It reflects fundamentally different approaches to uncertainty, evidence, and the pace at which knowledge should be constructed. When 3I Atlas began showing unusual spectroscopic signatures, this disconnect became particularly stark, with sensational headlines competing against methodical data analysis in what amounts to parallel universes of information. Consider the spectrum of media coverage that emerged as preprint papers began appearing on RxIve. At one extreme, tabloid-style outlets seized on the mystery aspects with headlines that practically vibrated with excitement. Alien craft disguised as comet baffles scientists read one particularly breathless example, transforming careful spectroscopic observations into science fiction scenarios with all the subtlety of a carnival barker. These outlets treated every unanswered question as evidence of conspiracy and every cautious scientific statement as proof that authorities were hiding dramatic revelations. More responsible science journalism struck a different balance, emphasizing the carbon dioxide dominance and unusual chemistry while acknowledging the limitations of current data. Publications like Life Science and Smithsonian Magazine managed to convey the genuine scientific intrigue without veering into speculation unsupported by evidence. Their articles explained why a carbon dioxide-rich coma matters, what nickel emission lines tell us about comet composition, and why scientists speak cautiously about preliminary findings. The contrast becomes particularly sharp when comparing these measured reports to official space agency communications. NASA and European Space Agency press releases stick religiously to established facts, orbital parameters, safety assurances, observing schedules, and instrument capabilities. Their language carries all the excitement of a technical manual, which serves the important function of providing accurate information while avoiding the kind of speculation that can later prove embarrassing if contradicted by additional data. This institutional conservatism creates information gaps that speculative coverage rushes to fill. When official sources limit themselves to analysis ongoing and further observations planned, more adventurous outlets feel free to explore possibilities that range from exotic chemistry to technological artifacts. The problem isn't necessarily that such speculation occurs. Science often advances through bold hypotheses, but that speculation and established fact can become confused in the public mind when presented with similar levels of apparent authority. The alien craft hypothesis provides a useful case study in how scientific caution gets interpreted through different media filters. The actual evidence consists of unusual but not impossible chemistry, an obscured nucleus, and outgassing patterns that differ from typical solar system comets. Responsible reporting presents these as interesting anomalies worthy of further study. Sensational coverage transforms them into smoking guns for extraterrestrial technology, as if the absence of conventional explanations automatically implies artificial origins. Social media amplifies these distortions through mechanisms that prioritize engagement over accuracy. Dramatic claims about alien visitors generate more clicks, shares, and comments than careful discussions of spectroscopic calibration. The algorithms that determine what content gets promoted have no built-in preference for scientific rigor, creating an information ecosystem where the most exciting interpretations often drown out more measured analysis. Even reputable outlets face challenges when reporting on evolving science. Carbon dioxide to water ratios reported as approximately 8:1 in early coverage might be revised to 6:1 or 12:1 as calibration methods improve and additional data become available. These revisions don't indicate that the original reporting was wrong, they reflect the normal process of scientific refinement, but they can erode public confidence in scientific claims if the iterative nature of research isn't clearly explained. The confirmation bias problem works both ways in this media ecosystem. Outlets that lean towards sensational coverage tend to emphasize any new data that supports exotic interpretations while downplaying findings that suggest conventional explanations. Conversely, more conservative outlets might underemphasize genuinely anomalous findings to avoid appearing credulous. Both approaches can distort public understanding by filtering complex reality through predetermined editorial positions. The peer review timeline creates additional complications for media coverage. Preprint papers appear on arXiv within days or weeks of observations, providing immediate access to technical findings, but without the quality control that comes from expert evaluation. Journalists working under deadline pressure might report preliminary findings as if they carry the same weight as peer-reviewed conclusions, creating situations where later revisions or retractions can seem like scientific flip-flopping rather than the normal evolution of understanding. Language itself becomes a battlefield in this process. When scientists write about unusual chemistry or mechanisms not yet fully understood, they're expressing appropriate caution about phenomena that don't fit established models. When media outlets transform this language into baffling scientists or defying explanation, the emphasis shifts from ongoing research to complete mystification, implying that the scientific process has reached a dead end rather than an interesting beginning. The trust tier that emerges from this analysis suggests a hierarchy of reliability that informed consumers can use to navigate conflicting reports. Primary sources, observatory press releases, peer-reviewed papers, official space agency statements occupy the top tier, representing information that has passed through institutional quality control. Secondary sources like established science journalism outlets provide valuable interpretation and context, but with varying degrees of speculative content. Commentary and opinion pieces, regardless of their quality, represent personal interpretations that should be clearly distinguished from established findings. Perhaps most importantly, media literacy, in the context of astronomical discoveries, requires understanding that "we don't know yet" often represents the most honest statement scientists can make about ongoing research. This phrase doesn't indicate failure or cover-up. It reflects the careful process by which durable knowledge gets constructed from incomplete information. In a media environment that rewards certainty and dramatic revelation, such intellectual humility can seem unsatisfying, but it may be the most valuable information of all. The challenge for consumers of science media lies in learning to enjoy mystery without demanding premature resolution, to appreciate the complexity of real research without losing interest when answers don't arrive on news cycle timelines. 3i Atlas will continue revealing its secrets on a schedule determined by orbital mechanics and observational opportunities, not by editorial calendars or social media trending topics. Chapter 9: The Carbon Dioxide Puzzle Box. The carbon dioxide shroud surrounding 3i Atlas operates like a cosmic puzzle box, where each attempt to understand one aspect of the chemistry reveals additional layers of complexity beneath. This isn't simply a matter of unusual composition, it's a systematic pattern of observations that challenges our understanding of how comets form, evolve, and interact with their stellar environments. The more we learn about this chemical veil, the more questions it raises about what lies beneath. The fundamental puzzle begins with production rates that seem almost inverted compared to typical comets. Most solar system comets produce water vapor as their dominant outgassing component, with carbon dioxide playing a supporting role. 3i Atlas appears to operate by different rules entirely, generating carbon dioxide at rates that dwarf water production by factors that strain the boundaries of what we consider normal for these ancient objects. It's like discovering a reverse snowman that's made primarily of dry ice with just a dusting of regular snow. This compositional inversion affects every aspect of how we study the comet. Carbon dioxide gas is optically thick at many wavelengths, meaning it absorbs and scatters light in ways that make it difficult for our instruments to peer through to the nucleus underneath. Unlike the relatively transparent water vapor comas of typical comets, 3I Atlas wears its carbon dioxide atmosphere like a chemical cloak, revealing only what it chooses to show us, and concealing everything else behind a dense, chemically active fog. The Ferex observations add another dimension to this puzzle by revealing what they don't show: obvious jets or streamers that would indicate active regions on the nucleus surface. Most comets develop asymmetric outgassing patterns as solar heating concentrates on areas with different compositions, orientations, or thermal properties. 3I Atlas, however, appears to outgas uniformly from its entire surface, creating the featureless, symmetric coma that makes it so difficult to study the underlying solid object. This uniformity might indicate a nucleus that's remarkably homogeneous in composition, with carbon dioxide ices distributed evenly throughout the object rather than concentrated in specific regions. Alternatively, it might suggest a surface layer or crust that regulates outgassing in ways that smooth out underlying compositional variations. Either interpretation points toward formation or evolutionary processes that differ significantly from the mechanisms that created solar system comets. The temporal evolution of the carbon dioxide production provides crucial clues about the underlying physics. As 3I Atlas moves closer to the Sun, increasing solar heating should drive changes in outgassing rates and chemical signatures. The emergence of cyanide emissions in mid-August, coinciding with the nickel detections, suggests that we're watching a complex chemical system respond to changing thermal conditions in real time. The geometry of observations matters enormously for interpreting these changes. Phase angles, the angle between the Sun, comet, and Earth, affect how we see both reflected sunlight and thermal emission from the nucleus and coma. A jet or active region that's invisible from one viewing angle might become obvious from another. This means that reports of no obvious jets must be understood as epoch-specific and viewing geometry dependent rather than definitive statements about the comet's activity patterns. Hubble's imaging constraints illustrate the observational challenges created by the carbon dioxide shroud. Even our most advanced space-based telescope can establish only upper limits on nucleus size rather than direct measurements, because the solid core remains hidden behind its own emissions. It's like trying to study a light bulb from inside thick fog. You can see that something bright is happening, but the details remain frustratingly obscured. The James Webb Space Telescope's infrared capabilities provide a different window into this chemical puzzle box. Carbon dioxide emissions that are opaque at visible wavelengths become more transparent in the infrared, allowing JWST to probe deeper into the coma and potentially glimpse features closer to the nucleus. However, even these advanced observations require careful modeling to separate genuine nucleus properties from the effects of the surrounding atmosphere. Production rate calculations become particularly challenging in this environment because they depend on assumptions about how gas escapes from the nucleus and expands into space. In a typical water-dominated coma, these calculations rely on well-established models developed from decades of solar system comet observations. 3I Atlas's carbon dioxide dominance means that many of these standard assumptions might not apply, potentially leading to systematic errors in our estimates of gas production and nucleus properties. The chemical implications extend beyond simple composition questions to fundamental issues about comet formation environments. If 3I Atlas formed in a stellar system with different temperature profiles than our early solar nebula, it might have condensed from a gas mixture with different ratios of carbon dioxide to water ice. Such formation conditions could exist around stars cooler than our Sun, or in regions of protoplanetary disks where carbon dioxide remains gaseous at temperatures that would freeze water. Alternatively, The carbon dioxide dominance might reflect post-formation evolution during the object's journey through interstellar space. Cosmic ray bombardment, exposure to interstellar radiation, and chemical processing over millions of years could alter surface composition in ways that affect outgassing patterns when the object finally encounters another star. The puzzle box nature of these observations means that solving one mystery often reveals additional questions underneath. Understanding the carbon dioxide production mechanisms might explain the uniform outgassing pattern, but it raises new questions about formation, environment, and evolutionary history. Explaining the chemical processing that creates such unusual composition ratios opens inquiries about the stellar systems and galactic environments that could produce such objects. As 3I Atlas continues its approach toward perihelion, the carbon dioxide puzzle box will likely reveal additional layers of complexity. The increasing solar heating should drive changes in production rates, potentially revealing jets or active regions that are currently masked by uniform outgassing. Different volatiles might begin sublimating as surface temperatures rise, adding new chemical components to the already complex coma composition. The ultimate resolution of this puzzle will likely require combining observations across multiple wavelengths, instruments, and observing epochs to build a complete picture of how chemistry, physics, and history combine to create the unusual object we observe today. Until then, the carbon dioxide shroud continues to guard its secrets with chemical determination, reminding us that the cosmos still holds mysteries that challenge our understanding of what's possible in nature. Chapter 10. If it's natural. The natural explanation for 3I Atlas's unusual properties weaves together threads of stellar evolution, planetary formation theory, and cosmic chemistry into a narrative that stretches our understanding of how diverse the universe's comet population might be. If we're witnessing purely natural phenomena, then this interstellar visitor represents a window into formation environments and evolutionary processes that differ dramatically from anything in our local cosmic neighborhood, potentially teaching us about the chemical diversity of planetary systems across the galaxy. The formation environment hypothesis begins with the recognition that not all stars are created equal. Our Sun formed from a molecular cloud with a specific composition, temperature profile, and chemical evolution history that determined what kinds of materials could condense at different distances from the developing star. A comet forming around a different type of star, perhaps a lower mass, cooler red dwarf, or a star born in a galactic region with different metallicity, might incorporate ices and dust with compositions that seem exotic from our solar system perspective. In such an environment, the ice line structure that determines where different volatile compounds freeze out of the protoplanetary disk could be dramatically different from our early solar nebula. Water might remain gaseous at distances where carbon dioxide condenses into solid form, creating a population of comets that are naturally carbon dioxide rich rather than water dominated. This environmental explanation doesn't require any exotic physics, just different initial conditions that reflect the diversity of stellar formation environments across the galaxy. The surface evolution scenario provides another natural pathway to the chemistry we observe. Over the millions of years that 3I Atlas spent journeying between stellar systems, its surface would have been continuously bombarded by cosmic rays, exposed to interstellar radiation, and subject to chemical processing that doesn't occur in the relatively protected environment of our solar system's Kuiper belt or Oort cloud. Such processing could create insulating surface layers that selectively regulate outgassing, allowing more volatile compounds like carbon dioxide to escape while trapping less volatile materials like water ice beneath the surface. This mechanism could explain both the unusual carbon dioxide to water ratio and the apparently uniform outgassing pattern. If space weathering created a relatively homogeneous surface crust with consistent thermal and chemical properties, The result might be the featureless symmetric coma that makes 3I Atlas so difficult to study. As the comet approaches perihelion and surface temperatures rise, this insulating layer might begin to break down, potentially revealing the more conventional water-rich composition that lies beneath. The selective nickel release mechanism remains more speculative, but not beyond the realm of known chemistry. In carbon-rich environments, transient metal carbonyls might form under specific temperature and pressure conditions, creating volatile nickel compounds that can escape into the gas phase while iron remains bound in less volatile forms. Laboratory studies of metal carbonyl chemistry suggest that nickel carbonyl can be more volatile than many iron carbonyls, potentially creating the selective metal release we observe spectroscopically. Alternatively, the nickel-iron decoupling might reflect compositional heterogeneity inherited from the comet's birth environment. If 3I Atlas formed from materials that were naturally enriched in nickel relative to iron, perhaps condensing from a stellar wind or supernova ejecta with unusual element ratios, the metal emissions we observe might simply reflect this exotic but natural composition. The size and structural constraints from Hubble observations remain consistent with a natural small body. The upper limit of approximately 5.6 kilometers for nucleus diameter falls well within the range of solar system comets, and there's nothing about the dust production or coma morphology that requires anything beyond conventional comet physics. The fact that the nucleus remains hidden behind its own emissions is unusual but not unprecedented. Some solar system comets also develop optically thick comas that obscure direct observation of their solid cores. The temporal evolution of chemical signatures provides strong support for natural processes. The emergence of cyanide emissions in mid-August, coinciding with the nickel detections and consistent with increasing solar heating, follows patterns we'd expect from thermal evolution of volatile-rich materials. If 3I Atlas were an artificial object, we might expect more complex or structured temporal behavior, rather than the steady increase in activity driven by straightforward heating as the object approaches the Sun. The comparison with 2I/Borisov offers both reassurance and caution for natural interpretations. Borisov proved to be entirely conventional in its chemistry and behavior, demonstrating that interstellar objects don't automatically imply exotic origins. However, the fact that two successive interstellar visitors have shown such different characteristics suggests that we're sampling a diverse population of objects with a range of formation histories and evolutionary processes. If 3I Atlas is indeed natural, it provides unprecedented insights into the diversity of planetary formation environments across the galaxy. Every unusual characteristic, from the carbon dioxide dominance to the nickel-iron decoupling, becomes a clue about stellar systems and chemical processes that we can't directly observe but can infer from their frozen remnants that occasionally visit our cosmic neighborhood. The natural story also carries implications for astrobiology and planetary science more broadly. If comets can form with such dramatically different compositions depending on their stellar environment, then the delivery of volatile compounds to terrestrial planets might vary significantly across different stellar systems. Understanding this compositional diversity becomes crucial for assessing the potential habitability of exoplanets and the likelihood that Earth-like worlds receive the chemical ingredients necessary for life. Mars-based observations planned for early October could provide crucial tests of natural hypotheses. If 3I Atlas shows the expected thermal evolution, develops asymmetric jets as its insulating crust breaks down, or reveals compositional changes consistent with multi-layer structure, these observations would strongly support natural formation and evolution processes. The natural explanation for 3I Atlas is satisfying in its scope and internally consistent in its logic. But, like all good scientific hypotheses, it makes testable predictions that can be confirmed or refuted by additional observations. The ultimate test will be whether this natural story can account for all the unusual properties we observe, or whether additional anomalies will emerge that push us toward more exotic explanations. Chapter 11. If it's not natural. The possibility that 3I Atlas might represent something beyond natural comet evolution requires careful definition of what would constitute credible evidence for technological origin, as distinguished from the kind of speculation that can flourish in data gaps. This thought experiment must be grounded in the same rigorous evidentiary standards that apply to any extraordinary scientific claim, while acknowledging that our current observations fall far short of meeting those standards. Credible technosignatures would need to be both unambiguous in their artificial nature and reproducible across independent observations. Engineered isotopic ratios that differ systematically from solar system norms might indicate nucleosynthetic processes that don't occur in nature, but such measurements would require precision beyond current spectroscopic capabilities. Narrowband radio emissions synchronized with the object's geometry or rotational period could suggest intentional transmission, but no such signals have been detected despite radio telescope monitoring efforts. Structured radar echoes might reveal geometric regularity inconsistent with natural formation processes. If 3I Atlas possessed internal cavities, regular surfaces, or organized structural elements, these might be detectable through radar observations when the object reaches closer distances. However, current radar capabilities are limited by the comet's distance and relatively small size, making such observations technically challenging even if artificial structures were present. Non-gravitational accelerations provide another potential technosignature, but these must be distinguished carefully from the outgassing forces that naturally affect comet orbits. Oumuamua showed anomalous acceleration that initially sparked speculation about artificial propulsion before being explained by asymmetric outgassing of hydrogen. Any acceleration anomalies in 3I Atlas would need to show patterns inconsistent with known outgassing mechanisms, perhaps too regular, too directed, or occurring at times when thermal conditions wouldn't support natural volatile release. The nickel without iron signature has been proposed in some commentary as potentially indicative of industrial processing, since terrestrial metallurgy does produce nickel-rich alloys with minimal iron content. This represents interesting speculation rather than established fact, and it faces the challenge that unusual chemistry doesn't automatically imply technological origin. Many natural processes can create element ratios that seem artificial from our limited terrestrial perspective. The absence of obvious jets or tails has also been cited as potentially suspicious, with suggestions that the uniform outgassing pattern might indicate artificial regulation of gas release. However, this interpretation requires ignoring the observational limitations imposed by viewing geometry, instrumental resolution, and the carbon dioxide shroud that could easily mask narrow jets or asymmetric features. Natural comets do occasionally exhibit surprisingly uniform outgassing, particularly when observed at modest resolution or unfavorable phase angles. What we definitively do not have are multiple independent lines of evidence, all pointing toward technological origin. The unusual chemistry stands alone, without corroborating technosignatures that would be expected if we were truly observing an artificial object. There are no radio signals, no geometric structures visible in imaging, no isotopic anomalies, no acceleration patterns inconsistent with outgassing. The absence of such supporting evidence doesn't prove natural origin, but it does place the burden of proof squarely on claims of artificial manufacture. A responsible evaluation of technological possibilities would require multimodal evidence collected across different types of instruments and analysis techniques. Spectroscopic anomalies would need to be confirmed by isotopic measurements. Chemical signatures would need to be supported by structural observations. Any single unusual characteristic could potentially be explained by natural processes we don't yet understand, but multiple independent anomalies all pointing toward artificial origin would be much more difficult to dismiss. The historical precedent of Oumuamua provides both caution and context for evaluating exotic hypotheses. Initial observations of that object's unusual acceleration and elongated shape sparked serious scientific discussion of possible artificial origin, including peer-reviewed papers exploring technological explanations. However, subsequent analysis and additional observations eventually provided natural explanations for most of the anomalous characteristics, demonstrating how easily extraordinary claims can emerge from incomplete data. The confirmation bias problem affects technological speculations just as much as conventional interpretations. When looking for evidence of artificial origin, it becomes tempting to interpret any unusual characteristic as supporting that hypothesis while downplaying findings that suggest natural processes. This psychological tendency requires conscious effort to counteract, demanding that technological hypotheses be held to the same rigorous evidentiary standards as any other scientific claim. Time-resolved observations across perihelion passage could provide crucial tests of technological hypotheses. If 3I Atlas were an artificial object designed to appear comet-like, we might expect its behavior to diverge from natural thermal evolution as solar heating increases. Conversely, if its chemical and physical evolution follows predictable patterns driven by increasing temperature and changing illumination conditions, this would strengthen the case for natural origin. Isotopic measurements represent perhaps the most definitive test of natural versus artificial origin. Every stellar system has a unique isotopic fingerprint reflecting its formation history and nucleosynthetic processes. Natural objects carry isotopic ratios that reflect their birth environment, while artificial objects might show isotopic signatures that reflect technological processing or material sources that don't occur in nature. Such measurements push current spectroscopic capabilities to their limits, but could provide unambiguous evidence for exotic origin if anomalous ratios were detected. The coordinated radio search efforts that have monitored 3I Atlas represent exactly the kind of systematic investigation that technological hypotheses require. The absence of detected signals doesn't definitively rule out artificial origin. Any hypothetical technology might not emit in radio frequencies or might be designed to appear natural, but it does eliminate one of the most obvious potential technosignatures. If we engage in the thought experiment of what discovery of genuine artificial origin would mean, the implications extend far beyond astronomy into fundamental questions about intelligence, technology, and our place in the cosmic community. Such a discovery would represent confirmation that technological civilizations exist elsewhere in the universe and possess capabilities for interstellar travel or communication. The scientific and philosophical implications would be profound enough to justify the extraordinary evidentiary standards that any such claim must meet. For now, the technological hypothesis remains an intriguing possibility that serves an important function in ensuring that we consider all reasonable explanations for unusual observations. But speculation must be clearly distinguished from evidence, and extraordinary claims must await extraordinary proof. Chapter 12. The Mission Temptation. The prospect of intercepting 3I Atlas with a spacecraft represents one of those tantalizing missed opportunities that will haunt mission planners for decades. A chance to study an interstellar visitor up close that arrived with just enough advance notice to make us realize what we could have done, but not enough lead time to actually do it. The physics of orbital mechanics and spacecraft design create a cruel irony. The more unusual and scientifically interesting an object appears, the more desperately we want to send a probe to investigate, and the more impossible such a mission becomes with existing technology and planning timelines. The reality of launching a bespoke interception mission to 3I Atlas confronts the fundamental limitations of current spaceflight capabilities. Designing, building, and launching a spacecraft requires years of preparation under ideal circumstances. The fastest planetary missions in NASA's history, including the New Horizons probe to Pluto, required nearly a decade from initial concept to launch. 3I Atlas was discovered in July 2025, with a perihelion date in late October, barely 4 months of warning for what would need to be the most rapidly executed deep space mission ever attempted. Even if technical challenges could be overcome, the velocity requirements for intercepting a hyperbolic trajectory object are staggering. Unlike solar system planets that follow predictable elliptical orbits, interstellar visitors arrive with excess velocity that our chemical rockets can barely match. Reaching 3I Atlas would require a spacecraft to achieve delta V, change in velocity, comparable to or exceeding the most ambitious missions ever flown, and to do so within a launch window measured in weeks rather than the years typically available for planetary missions. However, the astronomical community has not been sitting idle while 3I Atlas approaches its closest solar passage. Opportunistic observations using existing assets represent the practical response to this mission temptation. The European Space Agency's Mars orbiters, originally designed to study the red planet's atmosphere and surface, are being redirected to observe 3I Atlas during the comet's closest approach to Mars on approximately October 3, 2025, when the two objects will be separated by only about 30 million kilometers. This Mars-based observation campaign represents a compromise between the impossible dream of a dedicated interception mission and the limitations of purely Earth-based telescopy. From Mars's vantage point, 3I Atlas will appear significantly brighter and larger than from Earth, potentially allowing detailed observations of coma structure, nucleus properties, and temporal evolution that would be difficult or impossible from our home planet. The red planet essentially becomes a temporary deep space observatory, providing a closer perspective on the interstellar visitor without requiring a purpose-built spacecraft. The coordination between Hubble, James Webb, and SpaceMystery demonstrates how the astronomical community maximizes scientific return when physical interception isn't possible. These complementary observations across different wavelength ranges provide a comprehensive view of 3I Atlas's properties that no single instrument could achieve alone. Hubble contributes high-resolution imaging in visible light. JWST provides detailed spectroscopy in the infrared, and SpaceMystery adds wide-field context and additional spectroscopic capabilities. Public proposals to retarget existing deep space missions have surfaced in various forums, including suggestions to redirect spacecraft like Juno or other outer solar system probes toward 3I Atlas. While such ideas demonstrate creative thinking about utilizing existing assets, they face practical challenges including fuel limitations, communication constraints, and the fundamental physics of changing a spacecraft's trajectory from one target to another. Most deep space probes are designed with specific mission profiles that leave little room for major course corrections. The broader lesson emerging from this mission temptation involves the need for standing capabilities to respond to unexpected discoveries. Project Lyra and similar conceptual studies have explored what a rapid response interstellar object mission would require: pre-positioned spacecraft, advanced propulsion systems, and decision-making processes that can operate on timelines measured in months rather than years. Such capabilities don't currently exist but represent logical extensions of current space technology development. The Southwest Research Institute and other organizations have conducted preliminary studies of intercept mission architectures, examining the trade-offs between launch capability, propulsion technology, and scientific payload that would enable meaningful encounters with interstellar objects. These analyses suggest that while challenging, such missions are within the realm of possibility given sufficient advanced preparation and dedicated resources. The institutional dynamics around potential intercept missions reveal the conservative nature of space agency decision-making processes. NASA and ESA operate under budget cycles and planning horizons that are fundamentally incompatible with the rapid response times required for interstellar object encounters. Even if technical solutions existed, the bureaucratic and financial mechanisms for implementing such missions on short notice remain underdeveloped. Future preparedness requires not just technological development but institutional innovation, decision-making processes that can evaluate and approve missions on timelines measured in months, pre-approved budgets that can be rapidly deployed for unexpected opportunities, and international coordination mechanisms that can combine resources from multiple space agencies when extraordinary opportunities arise. The specific case of 3I Atlas illustrates both the promise and limitations of this approach. If Mars-based observations reveal additional anomalies or confirm the unusual characteristics already detected from Earth, the scientific community will have demonstrated that creative use of existing assets can yield significant results. However, many fundamental questions about the object's composition, structure, and origin will remain answerable only through direct spacecraft investigation. The timeline pressures created by interstellar object encounters also highlight the importance of ground-based and space-based survey systems that can provide earlier warning of incoming visitors. The earlier an interstellar object is detected, the more time mission planners have to evaluate intercept possibilities and develop appropriate responses. Projects like the Vera-C, Rubin Observatory and the proposed NEO-Surveyor mission could dramatically improve our ability to spot such objects with sufficient advance notice to enable meaningful spacecraft missions. Perhaps most importantly, the mission temptation generated by 3I Atlas serves as a reminder that the universe operates on its own schedule, not ours. Extraordinary opportunities for scientific discovery arrive when they arrive, not when we're prepared for them. The question facing the space community is whether we'll be better positioned to respond when the next interstellar visitor makes its appearance, or whether we'll once again find ourselves watching from afar as cosmic mysteries pass through our solar system and disappear forever into the galactic night. Chapter 13. The Calendar. Time moves differently for interstellar visitors than it does for those of us bound to Earth's daily rhythms. While we measure our lives in seasons and years, 3I Atlas follows a cosmic calendar written in gravitational mathematics, its schedule determined by the precise choreography of orbital mechanics, rather than human convenience or curiosity. Understanding this temporal framework becomes essential for appreciating both what we've already learned and what opportunities remain for unraveling its mysteries. The discovery date of July 1st, 2025, marks more than just the moment when automated telescopes at the Atlas facility in Chile first noticed an unusual point of light moving against the star field. It represents the beginning of a precisely defined observational window that will close forever when this interstellar visitor exits our solar system and returns to the galactic void. Unlike the planets, asteroids, and comets native to our solar system, 3I Atlas offers no second chances, no future orbital returns that might provide additional opportunities for study. The approach to perihelion, closest solar distance, scheduled for approximately October 30th, 2025, at roughly 1.4 astronomical units from the Sun, represents the climactic moment of this cosmic performance. At this distance, just inside Mars's orbital radius, 3I Atlas will experience maximum solar heating and presumably maximum activity. If the comet is going to reveal additional secrets about its composition, structure, or behavior, this period around perihelion offers the best opportunity for such revelations. The Mars geometry adds a crucial subplot to this temporal narrative. On approximately October 3rd, 2025, 3I Atlas will pass within roughly 30 million kilometers of Mars, a cosmic close encounter that positions the red planet as an opportunistic observation platform. This proximity offers European Space Agency orbiters currently studying Mars a unique chance to observe the interstellar visitor from a vantage point much closer than Earth's, potentially providing detail and perspective impossible to achieve from our home planet. The observational calendar, however, is complicated by the inexorable mechanics of orbital geometry. As 3I Atlas approaches perihelion and then begins its journey back to interstellar space, its apparent position as seen from Earth will bring it progressively closer to the Sun in our sky. Sometime in late September or early October, the comet will become too close to the Sun's glare for safe observation by most Earth-based telescopes, entering what astronomers call the zone of solar conjunction. This observational blackout period, lasting through most of November, represents one of the most frustrating aspects of studying 3I Atlas. Just when the comet should be at its most active and potentially most revealing, it disappears behind the Sun's overwhelming brightness from Earth's perspective. Space-based telescopes like Hubble and James Webb have some capability to observe closer to the Sun than ground-based facilities, but even they face limitations when targets approach too near our star's position. The emergence from solar conjunction in early December 2025 offers what may be our final extended opportunity to study 3I Atlas before it fades beyond the reach of current instrumentation. By this time, the comet will be receding from the Sun and likely decreasing in activity, but it will once again be positioned for observation by the full suite of Earth-based and space-based facilities that have been tracking its approach. This post-perihelion observation period will be crucial for understanding how 3I Atlas responds to decreasing solar heating. If the unusual chemical signatures observed during its approach, the nickel without iron, the carbon dioxide dominance, the cyanide emergence, show predictable evolution as the comet cools, this would support natural formation and evolution hypotheses. Conversely, any unexpected changes or anomalous behavior during the cooling phase could provide additional clues about the object's true nature. The preprint and peer review timeline adds another temporal dimension to this unfolding story. Scientific papers documenting observations from July through September 2025 have already begun appearing on RxEve, with initial findings available weeks or months before formal peer review. However, the definitive analyses incorporating the complete observational dataset, from discovery through final visibility, won't be available until well into 2026, long after 3I Atlas has disappeared from telescopic view. This lag between observation and complete analysis creates a peculiar information environment where the most interesting preliminary findings are available quickly, but must be interpreted with appropriate caution pending more thorough evaluation. The nickel detections, carbon dioxide ratios, and other anomalous characteristics currently represent work in progress rather than settled science, even as they drive public interest and scientific speculation. The James Webb Space Telescope, Hubble Space Telescope, and SPHERICS observing schedules operate according to their own complex cadences of target priorities, orbital constraints, and data processing timelines. Observations made in August might not be fully analyzed and released until October or November, creating situations where the most detailed findings about 3I Atlas's properties might not become available until after the object has disappeared into solar conjunction. Public communication timelines add yet another layer to this temporal complexity. NASA and ESA typically maintain conservative schedules for releasing observational results, preferring to allow peer review processes to run their course before making strong claims about potentially significant discoveries. This institutional caution, while scientifically responsible, can create information gaps that speculative coverage rushes to fill during the months between initial observations and formal publication. The safety reminder that threads through every official timeline discussion that 3I Atlas poses no threat to Earth at any point in its trajectory reflects institutional recognition that cosmic mysteries can spark public concern. By maintaining clear communication about orbital parameters and closest approach distances, space agencies provide reassurance while allowing scientific investigation to proceed without unnecessary alarm. Perhaps most poignantly, the calendar of 3I Atlas represents a cosmic reminder that the universe operates on its own schedule, indifferent to human convenience or preparation. This interstellar visitor arrived when it arrived, will reach perihelion when orbital mechanics dictates, and will depart according to the mathematics of hyperbolic trajectories. Our role as observers is to make the most of the opportunities provided, understanding that some questions may remain forever unanswered simply because the cosmos doesn't arrange its schedule around our curiosity. The turning of calendar pages toward late October and early December 2025 marks more than just the passage of time. It represents the closing of a cosmic window that will never open again. When 3I Atlas finally fades beyond the reach of our most sensitive instruments, it will carry with it whatever secrets we haven't managed to unlock, leaving behind only the data we've collected and the questions we've learned to ask. Chapter 14. Reading Between the Lines. The phrase, "what scientists aren't telling us," typically implies deliberate concealment or conspiracy, but in the case of 3I Atlas, it more accurately describes the careful boundaries between what can be responsibly concluded from current data and what must remain in the realm of speculation until additional evidence becomes available. The gap between public curiosity and scientific certainty isn't evidence of secrecy, it's a reflection of how knowledge gets constructed from incomplete information under conditions of genuine uncertainty. The pending question of nickel without iron robustness illustrates this distinction perfectly. Multiple independent teams using different instruments have reported neutral nickel emission lines without accompanying iron signatures in their spectra of 3I Atlas. This represents a genuine observational result that's been reproduced across several facilities and analysis methods. However, the mechanism that produces this unusual chemistry remains unknown, and the reproducibility across different observing epochs and geometric conditions hasn't yet been fully established. What would constitute definitive confirmation of this anomaly? The same spectroscopic signatures would need to appear consistently as 3I Atlas approaches perihelion and solar heating increases. Different instruments observing at different wavelengths would need to show compatible results. The temporal evolution of the nickel emissions would need to follow patterns consistent with thermal models of nucleus heating. Only when these multiple lines of evidence converge can the scientific community move from interesting, if true, to established phenomenon requiring explanation. The question of nucleus size and shape under the carbon dioxide shroud represents another pending mystery that illustrates the limitations of current observations. Hubble's upper limit of approximately 5.6 kilometers provides a constraint rather than a measurement, establishing what the nucleus can't be rather than what it is. The actual solid core could be significantly smaller, irregularly shaped, or possess surface features that remain invisible behind the optically thick coma. Future observations might resolve this uncertainty through several approaches. Radar observations, if the comet passes within range of planetary radar systems, could potentially penetrate the coma and map the nucleus surface directly. Thermal infrared observations might detect heat emission from the solid core that's less affected by gas absorption than visible light. Most intriguingly, if the carbon dioxide shroud begins to dissipate as the comet recedes from the Sun post-perihelion, direct optical observation of the nucleus might finally become possible. The jets and tail question highlights how observational limitations can create apparent mysteries that later resolve with better data or different viewing conditions. Current reports of no obvious jets or featureless coma must be understood as epoch, specific, and instrument, limited rather than definitive characteristics of the object. Jets that are narrow, pointing in unfavorable directions, or obscured by the carbon dioxide shroud, might become visible under different geometric conditions or with higher resolution observations. Mars-based observations planned for early October represent perhaps the best opportunity to resolve this uncertainty. European Space Agency orbiters positioned much closer to 3I Atlas than Earth-based telescopes might detect jets, streamers, or asymmetric features that are below the detection threshold from our home planet. If such features appear in Mars Vantage observations, it would demonstrate that the apparent uniformity seen from Earth reflects observational limitations rather than genuine absence of structure. The carbon dioxide to water ratio represents another measurement that exists in the uncertain territory between preliminary finding and established fact. Multiple outlets have reported ratios around 8:1 carbon dioxide to water, but these numbers come from analysis of single epoch observations that may not represent the comet's full compositional story. As solar heating increases toward perihelion, the relative production of different volatiles could change dramatically, potentially revealing a more conventional water-rich composition beneath the surface layer that currently dominates outgassing. Peer-reviewed confirmation of these ratios will require careful cross-calibration between different instruments and observing epochs, along with thermal modeling that can account for how changing solar distance affects the relative sublimation of different ice types. The precise numbers may shift as analysis techniques are refined and additional data become available, but the general pattern of carbon dioxide dominance appears consistent across multiple observational approaches. The cyanide emergence documented in mid-August observations provides another piece of this evolving chemical puzzle. The temporal correlation between cyanide detection and nickel emissions suggests we're watching a complex chemical system respond to increasing solar heating. However, the parent molecules that produce cyanide radicals, the specific thermal conditions required for their release, and the implications for overall nucleus composition remain subjects of ongoing analysis. The coordination between James Webb Space Telescope, Hubble Space Telescope, SphereX, and ground-based facilities represents an unprecedented multi-wavelength campaign to study an interstellar object. Each instrument contributes unique capabilities: Hubble's high-resolution imaging, JWST's detailed infrared spectroscopy, SphereX's wide-field coverage. But synthesizing these observations into a coherent picture of 3I Atlas requires careful attention to systematic differences between facilities and observation epochs. This synthesis process takes time, often extending months beyond the initial observations as teams work to understand how instrumental systematics, calibration uncertainties, and temporal evolution affect their measurements. The most complete scientific picture of 3I Atlas will likely emerge only in late 2025 or early 2026, well after the object has disappeared from view, but when sufficient time has passed for thorough analysis and cross-validation. Media literacy becomes particularly important during this period of evolving understanding. News summaries of preprint papers provide valuable accessibility to technical findings, but may inadvertently present preliminary results with greater certainty than the original authors intended. Commentary and opinion pieces, regardless of their quality, represent interpretive frameworks rather than established facts, and should be distinguished clearly from observational data and peer-reviewed analysis. The distinction between "we don't know" and "we can't say" reveals different types of uncertainty that affect scientific communication about 3I Atlas. "We don't know" implies that current data are insufficient to determine the answer, but additional observations might resolve the question. "We can't say" suggests that the data might be adequate, but that responsible scientific practice requires waiting for peer review, replication, or theoretical development before drawing conclusions. Both types of uncertainty reflect the careful process by which reliable knowledge gets constructed from partial information. In astronomy, where phenomena often occur on timescales and distance scales that preclude controlled experimentation, this conservative approach becomes particularly important for maintaining public trust in scientific institutions and avoiding the kind of spectacular retractions that can undermine confidence in the research process. The questions that will likely persist even after 3I Atlas disappears from view illustrate the inherent limitations of studying interstellar visitors with current technology. We may never know the exact composition of the nucleus core, the details of its formation environment, or the complete story of its journey through space. Some mysteries may remain forever unsolved, simply because the observational opportunities were too brief and the technical challenges too great for complete resolution. This acceptance of partial knowledge represents a mature understanding of how science operates at the frontiers of the possible. Not every question has a definitive answer, not every mystery yields to investigation, and not every unusual phenomenon can be fully explained with current tools and techniques. The value lies not in complete resolution but in the advancement of understanding, the refinement of questions, and the preparation for better investigations when similar opportunities arise in the future. Reading between the lines of scientific communication about 3I Atlas reveals not conspiracy or cover-up, but the careful work of constructing reliable knowledge under conditions of genuine uncertainty. The gaps in our understanding represent not failures of investigation, but the natural boundaries between what current evidence supports and what remains to be discovered. Chapter 15. Drift into Sleep. As we near the end of our journey through the mysteries surrounding 3I Atlas, the cosmic visitor that arrived from interstellar space wrapped in chemical enigmas and spectroscopic whispers, it's worth pausing to reflect on what this story tells us about our place in a universe far stranger and more diverse than we sometimes dare to imagine. Here is an object that travelled perhaps millions of years through the galactic void, carrying within its frozen nucleus the chemical fingerprints of stellar systems we may never see, only to grace our solar system with a brief visit that challenges our understanding of what's possible in nature. The nickel without iron remains a gentle mystery, reproducible across multiple instruments yet unexplained by current theory. Like a cosmic riddle written in wavelengths of light, it reminds us that the universe still holds secrets that don't yield easily to our most sophisticated analysis. Whether this unusual chemistry reflects exotic formation environments around distant stars, processing by interstellar radiation during eons of cosmic wandering, or mechanisms we haven't yet learned to recognize, it speaks to the diversity of conditions and processes that exist beyond our familiar solar neighborhood. The carbon dioxide shroud that conceals 3I Atlas's nucleus serves as a metaphor for the partial knowledge that characterizes so much of astronomy. We see what the comet chooses to reveal: its gaseous emissions, its dusty coma, the spectral signatures of molecules escaping into space, while the solid core that contains the answers to our most fundamental questions remains hidden behind its own atmospheric veil. This concealment isn't deliberate obscurity, but simply the way complex natural systems interact with the tools we have available to study them. The temporal evolution we've witnessed, from the quiet July discovery through the emergence of cyanide emissions in August to the approaching perihelion drama of late October, illustrates how astronomical objects exist in their own time, following schedules written in orbital mechanics rather than human curiosity. We are observers of a performance that began millions of years ago and will conclude when 3I Atlas disappears into the cosmic dark, leaving behind only the data we've managed to collect during this brief intersection of trajectories. The careful language of scientific communication, the analysis ongoing and preliminary results, and further observations planned, reflects not institutional secrecy, but intellectual humility in the face of genuine uncertainty. When confronted with phenomena that don't fit established models, responsible science proceeds with the kind of methodical caution that can seem frustrating to those seeking immediate answers, but that ultimately produces knowledge reliable enough to build upon. This is perhaps the most profound lesson embedded in the 3i Atlas story, that silence often indicates care rather than concealment, that unanswered questions represent opportunities for discovery rather than failures of investigation, and that the boundaries of our knowledge define not limitations but frontiers waiting to be explored. Consider the two narrative paths that remain open as we drift towards sleep. In one story, 3i Atlas represents the natural but exotic product of stellar environments unlike our own, a cosmic ambassador carrying the chemical signature of formation processes that operate under conditions different from those that created our familiar solar system. Its unusual properties become windows into the diversity of planetary formation across the galaxy, teaching us that the universe creates comets in ways we haven't yet learned to expect. In the alternative story, presented clearly as speculation rather than conclusion, 3i Atlas might represent something that challenges our assumptions about what occurs naturally in the cosmos. The combination of unusual chemistry, hidden structure, and anomalous behavior might point toward processes or origins that stretch the boundaries of conventional explanation, opening questions that could reshape our understanding of what's possible in the universe we inhabit. Both stories remain consistent with current observations, and both will likely persist until additional data tips the balance of evidence toward one interpretation or another. This coexistence of possibilities isn't a failure of scientific method, but an honest acknowledgement that complex phenomena often admit multiple explanations until sufficient evidence accumulates to distinguish between them. The observations planned for the coming weeks, the Mars Vantage studies, the perihelion monitoring, the post-conjunction follow-up, will add new chapters to this unfolding story. Each spectrum, each image, each measurement will either support or challenge existing hypotheses, gradually building the evidentiary foundation needed for confident conclusions. But even after 3i Atlas fades beyond the reach of our instruments, some questions will likely remain open, awaiting the next interstellar visitor to provide additional pieces of the cosmic puzzle. This is the nature of frontier science: partial answers leading to better questions, mysteries that reveal deeper mysteries, and knowledge that grows through the patient accumulation of observations and the careful evaluation of evidence. The universe operates on scales of time and distance that dwarf human experience, following physical laws that sometimes produce phenomena that seem impossible until we learn to understand them. As we let these questions rest for now, carried by the gentle current of cosmic time toward whatever revelations await, we can find peace in the knowledge that the same sky under which we sleep is crossed by visitors from distant stars, carrying stories written in chemistry and physics that we are slowly learning to read. The cosmos whispers its secrets in many languages, in nickel emissions and carbon dioxide shrouds, in orbital mechanics and spectroscopic signatures, and we are gradually becoming fluent in its vocabulary. Sleep well under the same sky that 3i Atlas is crossing on its journey from one stellar system to another, carrying its mysteries through the space between worlds. When you wake, it will be a little closer to perihelion, a little more active, a little more willing perhaps to reveal the secrets it has guarded during its long journey through the galactic night. The calendar pages turn toward late October 2025, when this interstellar wanderer will make its closest approach to our Sun before beginning its journey back to the cosmic void. Updates will come as data mature, as peer review processes run their course, and as the careful work of science transforms observations into understanding. But for now, in the quiet hours when the universe reveals its most profound truths, we can simply rest in the wonder of knowing that we share the cosmos with visitors from other worlds, and that some mysteries are worth contemplating in the gentle darkness that bridges our small lives to the infinite expanse beyond.